Hello, this is a video talking about universal gates. Before this video, you should have some knowledge about logic gates. So if you don't, please watch the video I created about logic gates. So let's do it. Okay, so what is a universal gate? Right? It seems like a big term, but it's basically just being able to create other logic gates using one logic gate. Okay, in our syllabus, we are taught using the NAND gate and the NOR gate. Okay, so what I'm saying is, using just a NAND gate, you can create every single logic gate out there. Using just the NOR gate, you can create every single logic gate out there. Alright, so okay, what gates can you create? Everything. You can create NOT gates, you can create AND gates, you can create OR gates, you can create NAND, you can create NOR, and you can even create XOR and XNOR. Okay, but unfortunately, for this video, I'm only going to be teaching NOT and OR, NAND, and NOR. I will not be teaching the XOR stuff for this video. Alright, so how do you go about doing this? Let's split up this paper canvas painting thing here. I'm going to show you how to create these gates using NAND first, then I'll move on to NOR. Okay, so let's start with the NOT gate. The NOT gate looks like this. One input, then into the two inputs of the NAND, and then one output. And that's it. Okay. It may not be obvious as to how this works at first glance, but let's draw a truth table. Okay. So let's label this as yellow, label this as red, so we can easily see what's going on. So, truth table, we have A, we have yellow, and we have red and X. Alright, so A is the only input here, so we just draw the possible combinations. And when A is 0, both yellow and red will be 0. When A is 1, both yellow and red must be 1. Okay, very nice. So, I'm very sure all of you know the behavior of a NAND gate. Let's draw out the truth table here actually, for future reference. Alright, 0, 0, 0, 1, 1, 0, 1, 1. Okay, when both 0, an AND gate will make it 0, but since it's inverse, it'll be 1. Okay, I'm just gonna fill it out. You guys should know this by now. Alright, the behavior is like this. So when both are 0, it should be 1. Nice. When both are 1, it should be 0. Boom! Inversion. Not gate achieved. Not gate achieved. Amazing. Okay, let's move on to the next one. Let's move on to the AND gate. Okay. Do you guys have any idea as to how I could do an AND gate? Since we have a NOT gate already, it's actually very simple. Okay, AND gate. We just take a normal NAND gate and we just inverse its output. Boom! AND gate. That's it. That's it. Let's move on to the OR gate. Okay, the OR gate. This is where it gets a bit confusing, but don't worry, I will guide you every step of the way. So it starts with inversing both inputs separately. So this is A, and then this is B. Okay, there is a thing here. Yes, and this is B. Then we NAND both of the outputs of this, and this is the OR gate. There. So how does this work? Okay, again, we can draw out the truth table. Let me label the output of this logic gate as red and output of this as yellow. So let's draw a truth table. Draw out all the possible configurations. Oh, I need to leave space for red and yellow. So let me go ahead and do that. Red and yellow. And then X. Alright, cool. So A is the inverse of red is the inverse of A. So we just need to, whenever A is 0, red will be 1 and vice versa. So this. And we can do the same for yellow. Okay, nice. Now we have this, which is the input for this NAND gate. So both are 1. Both are 1. What is it? Output is 0. 1, 0. Output is 1. The rest are 1. The rest are 1. The rest are 1. So after using a truth table, we can see now that the behavior of this OR gate is sound. This is an OR gate. And that's how that works. Okay, half of the lesson is done. Next half is I'm going to talk about how to create all the other gates with a NOR gate. Okay, a quick recap about the NOR gates is I'll draw the truth table. Okay, A, B, and X. Okay, so it's just the inverse of an OR gate, and that would be this. Nice. Alright, so let's see how to do a NOT gate. Okay, let me draw a partition here. Okay, so what's a NOT gate look like? Well, it's actually very similar to the NAND gate one. It's actually the same. That's it. This, okay, that's a B. This is the NOT gate. To just show that it's the same, let's just do out the behavior again, baby style. So truth table, A, yellow, red, and X. Okay, 0, 1, both must be 0, both must be 1. And we just look at the behavior. So when both are 0, it's 1. When both are 1, it's 0. Boom, NOT gate. Alright, now for the AND gate, which is the harder one to understand for this one. This is how it looks. Okay, this is how it looks. You inverse the first input. You inverse both inputs separately. And then you NOR everything. Let me fact check myself. Yep, that is the AND gate. A, B, X. So I'm going to go through how this works. Let's say green and gold here. Green and gold. I'll draw the truth table. Alright, so we have two inputs. We have green and gold. Yeah, green and gold. And then X. So let's construct this truth table. Alright, let's fill it up then. So green is the inverse of A. So whenever A is 0, we just make it 1 and vice versa. And same thing with yellow, but for B this time. Alright, cool. So now we can just compare this, since it's the input for the NOR gate, with the truth table of the NOR gate. So when it's 1, 1, okay, when it's 0, 0, it's 1. And then the rest is 0. And you can see this is the behavior of an AND gate. Boom, AND gate. Alright. Now the last one, which is the simplest one, NOR gate. At this point of time, I'm very sure you can answer as to how this will look like. It's just a NOR gate, and then you inverse the output using the NOT gate that we know. Okay, there is not enough space. Let me make this a bit smaller. Yeah, alright. And that's a NOR gate. Oh wait, OR gate. Sorry, OR gate. Yeah. Okay, so these are the universal gates that you must know for the exam. And yeah, that's it. Thank you for watching. Please revise your work. Goodbye.